Hello, everybody, and welcome to Control System Analysis and Design. This example is going to be a very fundamental, theoretical, low foundational intro to a steady state error within a system. So the way we're going to do it is we're going to break it down, and if you had only the tools that you've learned up to this point in controls theory, how would you find the steady state error for this system? So what we're going to do is, for the system, we have an output of y and an input of u. What you're going to do is, starting right off the bat, is you've got y over u is equal to k over s over 1 plus k over s. Because the output is k over s, but the input is 1, this circuit unity feedback, which is equal to 1, plus k over s, which is the part of the unity feedback also. So, moving from there, if you solve that out, get the common denominator and everything, you'll get k over s plus k. So this is reducing this block diagram up there to basically just a single block, just like this. That's what we just did right there. We created a single transfer function. So, in order to get the steady state error, which we're going to denote as E here, this is equal to the complete response of the system, a perfect system, 100%, minus whatever your system is creating that's junk, basically, or whatever your system is providing. And the difference will be the junk, this steady state error, because say you want an output of 1, which is 100%, but your system only comes up to 0.9, 90%. The steady state error will be 10% there. So, this is u. So, doing a little bit of math here, this is equal to 1 minus k over s plus k. Now, this isn't very useful at this point, so I'm going to get a common denominator here. So, we've got s plus k over s plus k, which is equal to 1 still, minus k over s plus k, is u. And this is going to equal s over s plus k. U. And that is your steady state error. That is the formula for your steady state error. So, moving on from there, say we have an input of a unit step, and as we should all know at this point, a unit step is a 1 over s. That is the input. So, in order to add that in here, if you were to put in 1 over s coming into this, then you would have unit error of an error, which is equal to E, which is equal to E of infinity, because the settling time, the final value, is what we're shooting for in order to find out how close it is to our shot here. So at infinity, the system has hopefully settled down to its final value, and that's where it's going to be for the rest of forever. So we use infinity there. That's the notation. This is going to equal the limit as s goes to 0 of s over s plus k, excuse me, there was an error made in this, the limit of s, unit step, of 1 over s, times the unit step again. So we've got the limit of s over s plus k, which is our normal transfer function over here, and then our input u, which is 1 over s, but then the limit of s as s goes to 0. Hopefully s is going to 0, because as you go to infinity, s is going to 0. That's how you take the limit at something of infinity. And s, this is the extra factor based on the condition of steady state error. When you're working with a unit step system, when you're finding the limit, you have to add in this extra unit, that extra s there. So, this is going to equal then s over s plus k, because hang on just a second here. Yeah, because these two cancel. I'm looking at my notes and I was confused for a second of what was going on with the notes. But okay, so s as s goes to 0, and this is going to equal 0, because you got 0 basically over a number. Because this s is going to go to 0, but you still have k, and this s is equal to 0, which is equal to 0. So that is your steady state error. So if you're shooting for a final value of 1 and your system actually takes you to a final value of 1, then you have a steady state of 0. Alrighty. That is just about all there. I could go into the ramp and everything else, but I'm going to actually just skip that because it's much more useful to see this. This table, let me get focused in on it here a little bit, so hopefully you guys can see it. Get in a little closer so it's useful to you. So if you have the Norman Nice book, Control System Engineering, you should have this table in here. And this table basically gives you a shortcut to what we just did. Instead of having to solve the system completely like we did here, now it's all blurry, you can go to this table, you can define what kind of system you have, type 0, type 1, type 2, and then figure out what kind of inputs you have, and then from that you can determine what your steady state error is. Is it infinity? Well, in this case, we had a type 1 system because it was K over S. I can't show you that, but K over S, which means you had one pole at the origin, and that's how you define the type. The number of poles at the origin is equal to your type. So we had one pole at the origin, so we were a type 1, and we had a step input, a unit step input. So at type 1 and a unit step input, your error is 0. And you could have done that by doing KP and everything else. And if you want to learn how to do this using just this table and learning this shortcut, you need to watch one of my other videos where I go over that a little more. Or ask your professor about this and he can give you more details on how this table works if you haven't been introduced to it already. This table is very handy in getting a lot of shortcuts. But if you want to derive error from the very basic thing and solving it only with the tools you have so far, let me get this up here, you can go through all this mess. And that's the fundamental theory of steady state error.